safety bar, and you talk about the degradation of carbon. There are what is called, your book doesn't really bring up the word well enough, it's called diagenesis. And diagenesis is the breakdown of carbon, breakdown of organic matter. And what are the steps involved with breaking down organic matter within the environment? Where does it go? How long does it stay in different areas? What happens to it? And this slide here does something really cool from what we talked about before with the TCA cycle, central metabolism. It says like starches, cellulose. What's the base unit? So when organic matter starts to break it down, what does it break it down to? Well, we talked about getting it, if you can get it to glucose, man, you can do glycolysis, you can write in TCA, you can do a lot of stuff with it. So organic matter, some microbial populations will break it down and push it into glucose, and from there, you know the process, you know the steps involved with it. But each one of these organic matter here, not only do these organic matter have carbon in it, but some of them will also represent good sources of nitrogen, phosphorus, hydrogen, oxygen, other things that can be utilized by the cell. So even though it's organic matter, like say starch, has good amounts of carbon and hydrogen. Proteins, we talked about this before, having very good concentrations of nitrogen. So if you need organic nitrogen, if you need nitrogen to rebuild yourself, the utilization of proteins, the breakdown of proteins, is a very good source for getting something like this. It says here, like lignin here, there is a breakdown process of it. It's just ridiculously slow. It's just ridiculously slow. Now, some of the other ones, you can see here, most of them will degrade with oxygen. Not all of them will degrade when it's anaerobic, just because there's less energy involved. Because once we take away oxygen, there's less energy. You're talking about electron donating processes here. There's just not enough energy to couple that reduction or that reaction with nitrate reduction, iron reduction. Now, I will say that of all things that we're going to talk about, this is changing. Because as we understand more about the electron transport chain, as we understand more about utilization of energy, we start seeing that this number changes, or this amount changes. Because now we start finding new bugs that do new things. And so that's evolving. And that's what we're talking about here. I've used the term mineralization before. Mineralization means breaking down the organic matter all the way out until it is now inorganic. And so CO2. So you break it all the way down and you get the organic matter all the way from the C6H12O6 glucose molecule all the way out to CO2. That's total mineralization. So that's what we're talking about with that. Then nutrient immobilization is another term that you put in here. That can be in terms of a couple different things, actually. But the main point of it is that it's no longer available. And this is a term that a lot of geochemists don't get, because they'll take a lump of sediment and they will dissolve it out and they'll say there is 1.5% organic matter here. In this other one, there's 1.2. This has more organic matter. Well, but if it's unavailable, if it's trapped within a rock, if it's bound to something that you can't break it apart, it may be unavailable. And so that's a key term when you're understanding the environment is, okay, it's there. There's a lot of money in the bank, but it's unavailable to me, right? So what's the point of saying, oh, I've got a lot of money? It can't get to it. What's the point of having a lot of nutrients or a lot of carbon if you can't get to it? So adding this term to your understanding of the environment is something that is evolving, is something that we're trying to understand better, because it's not available. What's the point of it? Another one is oxygen. Oxygen availability works in a couple different ways, in terms of either you like it and you're glad it's there, or you don't like it and you wish it wasn't. Because a lot of reactions, like I said, are not, the carbon, organic carbon is now not available because you're in an anaerobic condition. Or you're an organism that is susceptible to oxygen toxicity. We talked about those that are microaerophilic, we talked about those that are obligate anaerobes. So the availability of carbon and oxygen is very important to understand who can be in this environment, who can cycle some of those nutrients through. Here's the lignin degradation thing. I've already talked about that. You guys got that already. I was believe because I'm going to get to this climate change thing. We're going to talk about that. Nitrogen cycle, we've talked about the nitrogen cycle a number of times. We've talked about a number of different organisms that do nitrogen cycling. Nitrogen fixation, we talked about that. We talked about with cyanobacteria. We talked about that with rhizobium and rhizobiales, are groups that do nitrogen fixation. That's taking atmospheric nitrogen into and converting it to organic nitrogen. It's a very energy intensive process. It is susceptible to oxygen. It is carried out by aerobes and anaerobes, but nitrogenase is susceptible and is rendered inactive in the presence of oxygen. We talked about the nitrogen, the nitrosomes in cyanobacteria, and the heterocysts that cyanobacteria form in order to do nitrogen fixation in an aerobic environment, and you lock it away from oxygen in order to keep nitrogenase active. It's an anaerobic process in an aerobic world. It's the only way you can fix nitrogen is an anaerobic process. You do it aerobically if you lock it away from the oxygen. We talked about cyanobacteria doing that. Here's what I was talking about before about some circles. I know it's a lot, I know it's confusing up there, but if you break it down, it's actually really helpful to understand these circles. The red sides on these are oxidative processes. The black sides are reductive processes. The simple way to think about it is if you're adding oxygens on, you're oxidizing. If you're losing oxygens or putting hydrogens on, you're reducing. Right? So if you get that, you can see that ammonia is oxidized to nitrite. Nitrite can be further oxidized to nitrate. Nitrate can be reduced either back through nitrite and then to N2. It can be reduced to nitrous oxide. It can be reduced to organic matter because it's going to go to NH3. Organic matter generally is a degradation or decay process to liberate free ammonia here. Again, you can draw some lines and go through. This slide also adds nitrobacter, nitrococcus, nitrus ammonis, nitrus aspira, those bugs that we've already talked about. Now you see where they fit into each one of these different processes. But that's the nitrogen cycle in a nutshell. You've gotten the terms nitrification. You've gotten all that stuff. Let's move forward with it. Nitrate reduction is actually one of the key because it is second on the electron transport chain. First being oxygen, nitrate being second. There's a lot of research going into this. The other reason there's a lot of research going into this is because what do we use nitrate for? Where do you find nitrates?
Fertilizer.
Fertilizer. And since everybody and their cousin wants green grass and nice golf courses near waterways, there's a lot of nitrates that get dumped into our waterways, into our streams, lakes, estuaries, marshes, marine systems. There's a lot of nitrates. Well, these nitrates can cause serious issues because this can stimulate a lot of growth. This is a secondary reductive process. You have oxygen, then you have nitrate. If you start burning through the oxygen, you start burning through the nitrate, you have processed a lot of organic matter and you've gotten that area really scrubbed free of oxygen. Well, if you start really getting rid of all the oxygen in these environments, fish don't like it. Crabs don't like it. Other things that are tasty and economically important don't like it. And so there's a lot of research into understanding how to avoid eutrophication. Eutrophication meaning meaning good, trophication means lots to eat. So lots of good things to eat. When an environment has experienced eutrophication, then a lot of things are eating really fast and they burn up the oxygen. And you get dead zones, you get hypoxic zones, you get anoxia events, you get fish kills, you get nastiness along the coast. And the secondary player in that is this. So, part of the issue. Now, if you can burn a lot of this straight to N2, one good thing is that you get it to N2 and nitrogen leaves the system. And if nitrogen is leaving the system, it doesn't continue to cycle and continue to burn through more oxygen and more carbon. So if you can get it to go here, it's good. If it stays in the system, it becomes incorporated, it goes through anabolic processes, then
So other than cyanobacteria, what can you do it under aerobic conditions?
So cyanide is fixing nitrogen back
Right,
to
okay.
put it back into the system.
Okay,
So
what can you get rid of it with in anaerobic conditions?
in aerobic condition, well, so cyanos need other things as well. And one thing that cyanos can typically be limited on is iron. And so they will actually burn through the iron pretty fast. And so they actually limit themselves more because of iron than anything else. So they can fix their own carbon, they can fix their own nitrogen. So you can't be limited in the two things that you can fix. But if you blow out the iron, then you're in trouble. And that's where there's some ideas of pulling more CO2 out of the atmosphere by stimulating cyanobacteria by dumping iron in the oceans. And it does sort of work, but there's some other issues with it. But yeah. Anammox is an interesting one of those little side shunt processes where anammox is the anaerobic oxidation of methane. And we talk about oxidation processes as adding on oxygens. Well, the easiest thing to add on is molecular oxygen, O2. If you don't have the O2 around, you have to resort to something else. So you can oxidize ammonia anaerobically if you oxidize ammonia and you reduce nitrate, actually it's nitrite, NO2. So you reduce nitrite, you oxidize ammonia, and the end product is nitrogen gas, N2. And so there are some more research going into this to understand how important and how prevalent this process is for the removal of ammonia, the reduction of nitrites, and the production of N2. This is just a side pathway of it. Moving forward from there, and look at that cycle, look at this cycle, look at the picture, look at the circle, and you get all these little pathways and you see everything from it. Moving on now to iron. Iron is much more simple than nitrogen because either you are iron 3 here, or you're iron 2 here. And it just goes back and forth between 3 and 2, 3 and 2, 3 and 2. You can get it incorporated as an organic molecule. You can incorporate it in heme molecules into some enzymes will have iron associated with it. But for the most part, you're talking about going from iron 3 to iron 2, and iron 2 to iron 3. Oh, sorry, I did that backwards. Iron 3 to iron 2 because it's oxidative. It's backwards here. Iron 3 to iron 2 is reductive process. So remember, reducing, you get more negative. Oxidizing, you get more positive, because oxidizing, you're losing electrons. Reducing, you are gaining electrons. Right? You're accepting. You're the terminal electron acceptor. But that's it for iron cycling. Iron cycling actually does a fair amount in environmental systems in terms of, and this whole point of this is to mineralize carbon. Who's mineralizing that carbon? Who is degrading that organic matter? When the candy bar gets to the iron guys, this is what they're trying to do. Now, there is a wide range of microbes that will do this. The main problem with this is that technically we're iron reducers, because we have to reduce the iron from iron 3 to iron 2 in order to incorporate it within our cells. But we're not doing iron reduction for energy. And so when you're looking at microbial processes, you're looking at the environment, it is actually very difficult to determine, is that microbe using iron 3 for energy? And one way you have to do that is you basically have to starve it off of everything else, get rid of all the oxygen, all the nitrate, all the sulfur, everything else and whatnot that it can possibly reduce, and see if the stupid thing still grows. Because a lot of them, due to secondary reactions, and that's the reason why it says here, wide range here, due to secondary reactions, will just reduce iron because it's there. It dumps a charge, it's metal, it likes to pick up electrons, and it will reduce the iron just by itself. But that's the key thing here, is to observe to see if it's actually doing the respiration of it, actually reducing the iron. Because we are technically not iron reducers, even though we do reduce iron. We're not getting it for any energy. There is some cool things out there, like this bug that this magnetotactum here that can reduce or oxidize iron and form these magnetite. And that's magnetite is what that is. Iron 3, 4 is magnetite. Iron 304 is magnetite. The cool thing about magnetite